Hello everyone, I Nikhil welcome you to Vigyan Bharat. This is our fifth lecture in the real analysis course, and in this lecture today I'll be going to cover some of the most important exercises and results which comes under countable and uncountable sets. So if you are someone who is watching this lecture directly, I suggest you to first watch the first four lectures of this series, starting from countable sets, uncountable sets, and some important theorems and results in between that comes. So you first go through those four videos and then directly come to this. So let's move to our today's lecture. Here, if you can see, I have mentioned as what I have just told you the prerequisites which I required in order to understand this lecture. Today's lecture is divided broadly in three major categories. The exercises which we're going to do, which I'm going to discuss and give you some important hints in between wherever required. So the first level of difficulty is easy, and it's clearly understood that if you know the notion of bijection, what is a bijection map, that is a one-to-one correspondence from the set n of natural numbers to the corresponding set which you want to prove whether it is countable or uncountable. So such type of problems comes under this category. In the second category, we have problems which I have put it in moderate level. And finally, there are some important category. There are some problems which I have mentioned in the hard level. So let's quickly look one by one. And I just want to say you one thing, that if you are someone who want to get a good hold on the notion of countable and uncountable sets, if you solve each of the following coming exercises today in this lecture, in total they are 10. So if you solve these 10 exercises, there are higher chance that if you attempt some good competitive examination like CSIR net or GATE examination in mathematics or some good other related examinations, then definitely these 10 exercises will going to help you how to approach the problem directly. There will be some problems in between when you can use that result directly to solve the problem. So I suggest you to watch the video till the end. Okay, so let's now move ahead. Let's look at our first exercise of the day. What it says, that prove that the set Z is denumerable. Prove that the set Z is denumerable. Here this symbol bold Z represents the set of integers, this one. And by denumerable, which I have already covered in the previous lectures, it is same as countably infinite. So try to go through this notion in the previous lectures and try to prove this problem, solve this problem. What you are required in this, what you are supposed to do, that you have to establish a map F which is defined from the set of natural numbers to the set of integers, or it can be other way around also, from the set of integers to set of natural numbers, and try to prove that that function is both injective and surjective, that is both 1 1 and on 2. If you are able to find such a map, then this set Z is denumerable or countably infinite. I can give you a hint which will be very helpful for you when you'll be trying to prove this problem, that the set Z of integers is broadly, if I like try to, I would say there's a notion of partition. It comes when we study abstract algebra. Then what you can do is you consider all the elements of the set of integers, and you separate it in two parts. One, on the one part you consider all the even integers, and on the other part you consider all the odd integers, and try to find a rule which map uh, one some natural, like which map some natural numbers to the even integers and some natural numbers to the odd integers in such a way that this mapping is 1 1 not 2. Then you will be able to prove that. Okay, Now let's move ahead to the second exercise. So what it says in the second exercise, that you have to prove that the set n cross n, that is the Cartesian product. If you take the Cartesian product of the set of natural numbers with itself, then that set of ordered pairs where each element is a natural number is denumerable. And I assume you know what is the meaning of Cartesian product. If you don't know, I just write it for you. N cross n will be a set of this form. Collection of those, I would say, Mn, where these M and N are both coming from the set of natural numbers. For example, 1, 2 belong to n cross n. This is an element of n cross n. If I ask you that is 1 by 2, 0 belong to n cross n, the answer is no, because 1 by 2 is not a natural number. Okay, so again the idea is same, that you are supposed to find a map from the set of natural numbers onto this set of the Cartesian product n cross n, says that that map is 1, 1 and on 2. So try to construct such a map. If you are able to, then you are done. Okay. Now this third exercise for today is the most important exercise, which is often asked directly in the examinations, whether this set is countable or uncountable. So because you have to prove this, so again I would say that the notion which you are using here in order to prove the second exercise, you can try to construct a map in a similar fashion to prove that the set Q of natural numbers is denumerable or is countable. Okay? So denumerable means countably infinite. So you again try to construct such a map. That is, we know every rational. What you can do in order to prove 3, I would say you can do it in 3 ways. 3 ways in the sense that you try to prove 3 things, then Q would be automatically countable. If you are able to prove that, you know that I can write my set of rationals as the union of these 3 sets. Q plus the set of positive rationals, Q minus the set of negative rationals, and what remains is our 0, which is neither positive nor negative. So you try to prove first that this set, the set of positive rationals, is countable. If you are able to find a map which maps every positive rational, that is a by b, where this answer is positive, a by b is the quotient is positive, then it belongs to Q plus, because what happens, this a by b where these are integers, then this ratio a by b, this fraction, if both are positive, then again it belongs to Q plus. If both are negative, suppose say minus 1 upon minus 2, then the answer is 1 by 2. So it again belongs to Q plus. So collect all those elements of the form a by b where this fraction is belong to Q plus, and try to construct a map from the set of natural numbers to this set that it is both 1, 1 and not 2. So you have to find a rule which assigns such a map. And for this, you can study the Cantor's diagonal. It's called Cantor's diagonals. There's a result on like what he used. He used the concept of diagonals to prove that this Q plus is countable. So if you're able to do this, then try to prove in a similar way that Q minus is also countable. And finally, 0, singleton 0, there's which is a finite set, so we know a finite set is countable. So the union of these 3 will be Q, and we will be using this result here in order to prove that Q is countable. Fourth A, that is, I have A1, A2, A3, where A1 is my Q plus, A2 is my Q minus, and A3 is singleton 0. If I collect the union of these 3 countable sets, so the answer is countable, and so the answer is set of rational numbers, and that will be countable. So try to prove that. Okay, that would be more than sufficient for you. Let's now move ahead to this moderate level. Let me just first drop this one because it is not required right now. Okay, looks fine now. This fourth result is very important, because what happens in examinations, we use it directly. So try to understand the fourth exercise very carefully. But you are given a1, a2, an be countable sets. That is, you are given n countable sets a1, a2 till an. Now you have to prove these two. In the first one, you are supposed to prove that if I collect the union of these countable set, then the union is again operation which we apply on sets. So I apply on these n countable sets. So the resulting answer is again a set a1 a1 union a2 union till an. This is a set again. Now this set is again countable. You have to prove that. In the second, this is very again important for us, that in this one you have to prove if I take the Cartesian product of n countable sets, then the resultant set is again countable. That is the Cartesian product of finite, I would say the Cartesian product of finite number of countable sets is countable. You can say it like that. And in the first case, in the fourth A, you can say the countable union. I would not say countable. I would say the union of a finite number of countable sets is countable, because countable union is the fifth. This result. This is again very important. This is very important for you. What it says, what you are trying to do in this one, fourth A, the problem above, you are trying to generalize it to a countable collection. That is, suppose you have a collection of sets which is countable. Of course, each element in this collection is countable, but the number of sets which you are considering is a countable number of sets. That is countably infinite, maybe. So that if you collect the union of all those, if you collect the union, then the resultant set of union is again countable. Try to understand this. That is, if am is a countable, am is countable for every m coming from the set of natural numbers. That is, if you fix m equal to 1, that a1 is countable, m equal to 2, a2 is countable. So for every choice of m, the resultant set am is countable. Then you have to prove that if I collect the union of all these, then that is again countable. This is a very important result for us. Okay, so now let me move ahead to criteria for infinite sets. I know by definition that a set is not that set is infinite if it is not finite. Now there's a criteria which you can use to prove whether a set is infinite or not. So what this criteria is, using the sixth, what it says, that a set is infinite if and only if. This is known as if and only if. Yesterday I was doing a video on set theory in which I have very in brief defined what it means. So if you don't know, you can refer to the last video which is uploaded yesterday. So if and only if means both ways inclusion. That is, if P and Q are two conditions and you want to verify that it is true both ways, that is P implies Q and Q implies P. If such condition hold, then we say P if and only if Q. That is, both are true simultaneously. So on the left of this symbol, this is your P. On the right on the symbol, this is Q. But P says that prove that a set is infinite. If you assume that your given set is infinite, then you should try to prove that it is equivalent to a proper subset of itself. I assume you know what is the meaning of proper subset. Proper means that again it's a subset. A is a subset, A is a proper set, A is a proper subset of set B if there exists at least one element in the set B which is not a member of the set A. So what it means, basically there are some at least one more element in the superset which contained its subset, so that which is not in the subset, which is not, that element is not in the subset. So such a set is said to be a proper subset of that superset. Okay. So what it says that if you want to prove that a given set is infinite, you try to prove that it is equivalent to a proper subset of itself. What I'm trying to do is remove some of the elements from that infinite set. Then the proper subset which you have now is you try to have to prove that it is equivalent to the original set. So what you try to do, you try to construct a map from this proper subset to the original infinite set in such a way that the map is both 1, 1 and 1, 2. That is bijective. If you are able to do that, then your set is infinite. It can be said in another way that what I have just explained, that you try to construct a bijection between the set n of natural numbers and a proper subset of itself in order to prove that this proper subset is infinite, because we already know that this set of natural numbers is an infinite set. This information is already known to us. So if you want to prove that some set is infinite, you try to construct a map from the set of natural numbers to that proper subset, which you want to prove that it is infinite. In this particular case, I am restricting this problem to the proper subset of the natural numbers. Okay, but in the sixth case, what I was saying that it can be any infinite set in general, and I'm just trying to construct a map which is equivalent to one of its proper subset. Okay, let's now move ahead to these problems. Now, here you have to do some good amount of work, and some good results will be used in between in order to prove these difficulty level, the level which the problems which comes under this hard level. But I would say that if you are able to prove all these, then you will be not only going to learn the notion how these are countable and uncountable, so many important results you will going to learn simultaneously. So at least try to attempt each and every problem, and wherever you have any doubts, you can send me your solutions in the Telegram group, whose link you can find in the description of this video as well as the about section of the channel. So try to solve these problems and post your solutions over there, and if whatever you have any doubts, send your doubts and queries over there. Also you can write it in the comment box, but Telegram group would be better so that we can have a discussion over there. Okay, now the seventh problem, one of the most elegant problems for in the concept of uncountability. When we study uncountability, so this is the very first notion which we're trying to prove, that the set R of real numbers is not countable. Is not countable. Not countable means that it is uncountable. What it means in another way, that you cannot able to find a bijection from the set of natural numbers to set of real numbers. You will not be able to find any map. So try to prove this using the method of contradiction. Assume that there exists such a map, and at the end, when you will be going to proceed, you will find that that map is not bijective. Okay, now problem number 8. But it says that you have to prove that the unit interval 0, 1 is uncountable. In the problem 7, you have proved that the set R of real numbers is uncountable. In 8th, you are now trying to prove, I would say, an equivalent version of that. If you are able to prove that the set 0, 1 is uncountable, then it is almost same as proving the set R is uncountable. And that's what now the ninth result problem, which I have just noted here, that try to prove that the open interval 0, 1 is equivalent to the set of real numbers. That is, you can able to find bijection, one-to-one correspondence between the open interval, this 0, 1 open interval, and the set of real numbers. Both are uncountable. Okay. Now this 10th is a very, very, very important, I would say, very important result. If you are able to prove this, so many problems you are able to directly solve without without taking pen, you can directly mark them in the competitive examination. So what it says, let's read it. Prove that the open interval 0, 1 can be put in one-to-one correspondence with the set of all functions f, with the set of all functions, where these functions are of this form, that they are defined from the set of natural numbers to a set which contain only two elements, 0, 1. This of this consisting of this set 0, 1. So if you collect all those functions which are defined from set of natural numbers to this set of elements, set which contain only two elements, 0, 1, then if you collect all those maps, collect all those functions, then you can put this collection of these maps in one-to-one correspondence with this open interval 0, 1. And from the above exercises, we know that this open interval 0, 1 is uncountable. So the collection of all such maps which are defined from the set of natural numbers to this set, which consists of two elements, 0, 1, is uncountable. Okay. Excuse me. Okay. So these are the 10 important exercises which I ask you to at least try to attempt these exercises. you will not be able to reach to their complete solutions or proofs in the very first go, but at least you should try to attempt each and every exercise. And if you like have you stuck anywhere, if you have any doubts anywhere, then you can again reach out to me at the Telegram group, whose link you can find. And also we also have our official number, whose details you can find in the about section, as well as there's an email ID. You can send me an email also if you have any queries. And that's all for today's lecture. If you find this video to be useful and interesting, that I ask you to at least give us a like for this. And do you may share about the initiative, about the content which we are making among your friends, so that they can be equally benefited. And if you're new to our channel, then please definitely do subscribe it. And thank you so much for watching, and we'll be meeting again. Some good videos, lectures coming your way on the real number system. We'll be now moving ahead with the set of real number system that would be a base for this course, for the further coming topics like sequence and series and some good important notions. Okay, so thank you so much.